I'm Tom, I work at Cradle. We make plugins. Go check out our stuff. So the talk is mostly focused around C++ and some C++ classes, but I hope that the general ideas could be applied if you're using other low-level languages. So we get this kind of ubiquitous advice when we're doing audio programming, which is don't allocate memory on the audio thread. And I first encountered this advice in this really good article by Ross Benzina, and it introduced to me the idea that you can't do anything that has a kind of unbounded latency. So obviously no network access on your audio thread. Don't do that. Don't try and read from files, especially when you have a spinning hard disk like I did when I read this advice. Don't try and take locks. If you try and take a lock that's held by a lower priority thread, then you're at the mercy of the thread scheduler at that point. But when I got to this point in this list where it's like, no allocation, you can't allocate memory, that kind of blew my beginner mind, not in a good way as well, because I was using memory allocation all the time to do anything useful. But on reflection, this kind of makes sense, right? Like we're using a kind of a global resource here that's shared by all your threads. And so there's going to have to be some kind of lock or synchronization in there. And, more generally speaking, we just don't really know what's going on in the system allocator a lot of the time, especially if we're making multi-platform software. We have to deal with different system allocators. We can't really rely on anything in there. But, it's so tempting. There are so many great reasons to allocate memory. We do it all the time when we're not on the audio thread. Reasons we might want to do it in our audio code, get buffers for capturing audio data or MIDI events. We often keep temporary buffers for like incremental or partially completed computations. Sometimes we like to arrange our DSP as a graph with nodes, and we want to change that graph while it's running, add new nodes, add new connections, remove things. And that generally requires allocations. So loads of great reasons to do this, but we're not allowed to. So, we come up with workarounds. Like sometimes we just skip the feature, it's too much work, or it's too much maintenance. Sometimes we pre-allocate things when we initialize, so we might pre-allocate buffers to write into. We might do this thing where we create a pool of objects, like a vector or something, of 100x. So when I need one, I can get a reference to that. And we might have to make choices at that point about how many to pre-allocate. We need to track which ones are in use and which ones aren't. We need a pool for each and every kind of thing we want to use. We might do something more sophisticated where we send a message to a background thread, which does the allocation for us and then sends something back. All this stuff works, we've been doing it, and it's useful, but there's so many decisions to make at all these different points. It's hard work, it's hard brain work. There might be some cases where there's an easier way. So, our problem with using the global allocator back then was, it's global, and we can't rely on its characteristics. So, what if we just had our own allocators? They could have blackjack and stuff. So we could guarantee the characteristics of those allocators. We could fine-tune them for our use case. We could guarantee that we're going to use them on one thread only, so we don't have to worry about locks. So obviously, we've kind of been able to do this forever, essentially. I think since C++ 98, we've had all our containers have an allocator template parameter, which we normally don't think about. We just say vector of t. But when we do that, we're getting a default allocator which uses the global heap. So we can put our own type in there and get our own allocator working on this container. But it's quite difficult to use this. Now anything that takes that vector of t also has to be generic over the allocator type because we've embedded it into the vector. And it was really hard to write one of these and use one. There's this hairy thing called allocator traits, which is, brain melting to read. And so not many people did it. There's good talk about the history of this by Pablo Halpin, which is, going through how things ended up this way and what the way forward is. So the way forward, we think, is a thing called std_PMR, and it landed in the C++ 17 standard. And that's a namespace, by the way, PMR. And it's an acronym for Polymorphic Memory Resource, which kind of gives you a clue how we're going to get around these limitations. So we're going to pay the cost of a virtual function call. And this is done in a way that's backwards compatible with the old way. This is going to fit into that template argument parameter, but we're not going to have that explosion of types. So you can get this by just including the memory resource header in MSVC and GCC. But if you're on Clang or you're using libc++, it's still in this experimental area. And the reason for that is because it's unfinished. There's some type definitions and things in this header, but the concrete implementations we're going to use are missing. So we've got your back. We ran into this immediately. We used Clang. And so we've implemented a backfill, a partial backfill. We haven't got everything that's in the standard, but we've got all the things we found useful for real-time software. You can get it at that address. The address will come back later if you haven't got time to write it down now. And it's MIT licensed, so you can use it in commercial code. So let's look at what's in this namespace. The first thing is a type of thing called a memory resource, and that is an abstract base class. It's an interface, and this is the thing where your memory comes from and where you give it back to when you're finished with it. And there are various concrete types promised by the standard, but not always there when you need them. And then there's this other thing called the Polymorphic Allocator, which isn't really polymorphic, and it doesn't really do much allocating either, so I'm not sure about this name. What this thing is, it's just a handle. It just holds a pointer to a memory resource. So this is where that virtual function call comes in. And this is what goes in that template argument of your containers. And its job is to be a stable type, so we don't get that explosion of types. Everything that uses a custom allocator can now just have that one polymorphic allocator as its second template argument. And it just holds a pointer. So it's small, it's cheap to copy. It adds, the size of a pointer to the stack size of your container. So you can usually ignore that. And then finally, there are just some type defs, which are for convenience, and they just type def the regular standard containers with a polymorphic allocator in that template argument. So this is what the memory resource interface looks like. Obviously, trimmed away lots of constructors and whatnot, but the core of it's really easy to understand. It's certainly a lot easier to understand and use than the allocator traits were. It does just what you'd think: allocate, deallocate, and there's an equality check thing. So let's look at some of the concrete types that the standard is promising to give us. So the first three of these are in the standard, and we have kind of backfills that should be drop-in replacements. When Clang or libc++ gets these, you should be able to just delete your dependency on our library and just switch some namespace names. The last one's like an extra goodie. It's not in the standard, but we found a need for it, so it's in there as well. And oh, by the way, for these type names, just stick _resource at the end. I didn't have space on the slide, so that's new _ delete _resource, and so forth. So the columns are a bit cryptic, but I'll explain what they mean. Recycling, can this thing reuse memory? If I hand back a block of memory, can it then be reused later? The speed, that's just a completely hand-wavy, relatively, on average, how fast are these things to find me a block of memory that I need. The overhead, that kind of refers to memory overhead. So some of these do some kinds of bookkeeping, and that is going to add a little bit to each allocation you do. The layout, that's like once you've finished allocating your objects, how are they actually laid out in memory? Because knowing that property, we can get some performance wins. So yeah, the first one, the new delete resource, it just uses the global heap. Like before, you've gained nothing, except for we're now in a much nicer world. We can swap this in and out with other implementations. And being the global resource, we don't know a lot about how it works. The monotonic buffer resource, that's often known, it's a type of thing that's often known as a bump allocator. So this thing just has a big, huge block of memory and a pointer. And when you want some memory, it just bumps that pointer forward and it returns the block that was skipped over to you for you to use it. And that's very incredibly fast. It's like effectively free. This thing doesn't store any information about the allocations it's done. So there's no memory overhead. But of course, the flip side to that is this thing cannot reuse memory. Once you've allocated something, if you try and hand it back, it just does nothing. So this thing will keep growing and growing and growing. And your objects are laid out, in that contiguous buffer. So that's obviously got some performance implications. The unsynchronized pool, there's a synchronized version of this which has a lock in it, but we're not interested in that, so it's not implemented in our backfill. And this is sometimes known as a slab allocator. This thing has a bunch of slabs of memory, and each of those has slots, and the slots are all the same size in a given slab. So that makes it very fast to find a slot to get memory from. You just jump to the slab that contains the right slot size, and then you can find a slot very quickly. So that's fast to allocate. There's not much overhead or bookkeeping involved, but because the slots are all the same size, if your object's 38 bytes or whatever, it might need to go in a slot that's 64 bytes in size. So you're wasting some of that memory there. And the layout, your objects of similar sizes end up packed quite tightly together in the same slab. But if you're allocating objects of different sizes, they're going to end up in different slabs and they're far away from each other. The last one, this is our one, but of course it's just a classic memory allocation algorithm, a free list. It's kind of slow because you're jumping over a linked list of blocks, and you need to store a little bit of information about each allocation. So there's some bookkeeping involved. And you can get this kind of fragmentation, diffusion thing where as you allocate and free things, you end up with gaps in your memory at different points, and your stuff just kind of diffuses across this block of memory. So there's this important concept within this world of chaining resources together. So some of these resources, like the slab, for example, needs memory to do its thing. So where does it get that from? You can pass it a resource, another memory resource, which it uses to get its own memory. Or maybe if it says I'm done and I'm used up, it can then use that upstream resource, is what the standard calls it, as a kind of fallback. And obviously, you're going to need something at the top of the chain or the end. That's often a new delete resource, this global thing. It might also be a null memory resource, which doesn't actually allocate anything. What this thing does is, as soon as you ask it for memory, it just throws an exception straight away, a bad alloc exception. And that's actually kind of useful for us because if we've got a static memory resource and we want to say, when we're done, when we've run out, we just want to stop and say, we're in a bad state now. You can just have this as the top upstream resource. So when your static stuff runs out, this thing's just going to throw an exception. and tell you, game over. So we're just going to look at a couple of like configurations of these things that you might use. The first one, very simple, just a monotonic buffer fed by a static buffer. So you allocate something up front and you give it this as its kind of source. And this is incredibly fast to allocate new objects. When you're done with all of your objects, it's very fast to clear the whole thing. If those objects are trivially destructible, you don't need to call their destructors, you can just reset that pointer to the beginning of the buffer. Again, it's practically free, but as I said, you can't deallocate individual items. So this is perfect if you're building up some kind of collection that isn't going to change its structure once it's built. It's there. Obviously you can modify stuff within those elements, but you can't, you don't really want to add or remove things because you're going to start wasting memory. But everything is in that linear buffer, and so if you're iterating across elements, your cache is going to be very hot, and you're going to be hitting it every time. Another configuration that we found pretty useful is the pool or the slab allocator fed by a free list. And this is useful because they kind of have opposing strengths and weaknesses. The pool resource is very good for allocating lots of small objects, and the free list is quite good for allocating or rarely allocating large objects. It's got quite a lot of overhead and stuff, but it gives you the precise amount of memory you ask for. So, if you're allocating lots of small objects, but occasionally large objects, you can say to the pool, hey, don't use a slab for anything larger than, whatever, 16K. Anything bigger than that, just call up to the free list and let that serve that part of the memory. So this is a really good general purpose pattern. You can do all kinds of things with it, building up strings, physics simulations. If you had lots of particles, for example, that might come into being, have a lifetime, and then die, and you want to keep reclaiming that memory, it's pretty good for that. You could run a scripting language off this. If you have a scripting VM that has like a pluggable allocator, this would probably be a pretty good candidate to plug into that. So it's not all plain sailing. Like we can't do our victory lap just yet because there's a few details that don't quite work for our use case. So the first one is that the polymorphic alligator. Yeah, that puts a new spin on that first lesson in object inheritance. So it's not propagating. So if you copy a vector or any container that's using the polymorphic allocator, the copy doesn't acquire your original allocator. So it's actually going to take, I think, the default memory resource. You can set this global default memory resource, but that's by default going to use the global heap. So now all of a sudden, if you push back to vector 2, you're going to potentially use the global allocator. And that's not what we usually want. I think this is a bit surprising, but I could actually see it being surprising the other way as well. So I can understand why the standards committee just kind of picked one. So our solution to this, we have a propagating allocator. We have a propagating allocator. I wish these names would just be a little bit easier to get your mouth around. This works just the same way as the polymorphic allocator, but it does propagate when you copy some container or other. And this is another free goodie that's in our real-time memory library, but it doesn't exist in the standard. And then you need to go and redefine your container type defs so that they're using this propagating version. Another problem. Once you've got this, you start to use containers and collections everywhere in your audio code that you used to be quite hesitant about. But it would be really easy to leave off that PMR namespace. It might slip through a code review. So how can we catch that? We have got some unit tests where we override global operator new, and we have this like allocation notifier, which will kind of emit an event or something when anyone uses the global new and delete operators. So you can wrap your tests in one of these things and just check that nothing is using the global heap. You could even wrap an entire suite of tests in this, for example. And then there's the final problem, like the ultimate problem, which is that we haven't actually solved this problem in a complete way. I said before that you might do pre-allocation or do your own object pools and they can run out. Well, these can run out too. We haven't solved that ultimate problem. If you've got the null memory resource at the top of your chain, then when you run out, it's going to throw an exception, which leads to this kind of slightly weird code that we're a bit uneasy about, where you wrap your top-level audio processing in a try-catch. And we try not to use exceptions in audio code because they might result in an allocation. But so here, we get uneasy. But of course, if we're in this situation, then we've already run out of all the memory that we sort of designated for our real-time use. So this does represent a truly exceptional situation, and it's time to take evasive action if this happens. So don't really have a true solution to this one. We've kind of kicked the can down the road or down into the allocator. One thing you could, think about doing if you're not too worried is just fall back to the new delete resource. It's not, it's not a very good solution because you could be glitching if you end up using this. But you might prefer to just take that risk instead of shutting down everything when you run out. Probably the best solution that we haven't yet got around to addressing or trying might be to have an allocator that has its own background thread, and it just watches, to see if we're close to running out of memory, and it's going to quickly head off, grab some more for us, and swap it in. Maybe you might use one of the techniques that we've seen at the conference, like Timur's read, copy, update paradigm. So whether or not this is it could still run out, right? If that thread doesn't allocate you more memory in time, then you're still back to square one. But if your user is just dragging things with their mouse, it's unlikely they'll beat the thread. If you let them sort of type 1,000, DSP nodes, please, and hit enter, then maybe you will beat the allocator, and you're back in trouble. So I haven't really talked much about performance because I'm more interested in this for the code cleanliness and kind of ergonomics that it offers. But there are wins available here because we all know that cache coherency is the king when it comes to performance on modern CPUs. So you know how your memory is going to be used. So if you design your allocations and your allocators appropriately, you can do a better job than the global allocator can of guessing how those patterns are going to be used. So I think a good example is if we had that graph of DSP nodes. If we normally process DSP nodes in a kind of topological order. So if we actually allocate them in a topological order, then they're going to be right there in a linear buffer, one after the other. And as we process them, we're just blasting through that linear buffer, and we're always hitting the cache. It's really easy to benchmark different setups because you don't need to change any of your types. You just insert a different memory resource pointer. I haven't got any lovely performance graphs for you. It would be totally pointless because there's this great talk by John Lakos. It's a two-part talk, and I think the second part is just stuffed with graphs and performance analyses. So, just go watch that talk if you're interested in what this can do for you. So, there's lots more material on this. There was obviously a raft of talks in 2017 and around then, all at CPPCon. Pablo Halpern, I've mentioned, John Lakos, I've mentioned. They're all exploring different aspects to what this can do for your code. It's quite a powerful idea. And Jason Turner did a bunch of talks on his YouTube channel, where he's just kind of prodding it and trying it out. You know, what happens if I customize the allocator of a JSON library? Like, how much speed can I win from that? And lots of other stuff in there. So it's time for me to say thank you. Thank you to you guys for coming, and thank you to Steve, who's the co-author of that library that we've made. That's the link. So please, get on there. We're not experts in writing memory allocators, so please make contributions, PRs, and yeah, go ahead and use it. Thank you.
Hi. Yeah, interesting. I've got 2 quick comments. I might have forgotten them in that space of time. One of them in terms of your fallback. There was an interesting post by Vector of Ball. I don't know if you caught this a few years ago, where he used mmap to allocate just like 100 gigabytes. And then just uses that as essentially a monotonic source, and just lets the memory architecture deal with how to manage it. So that could be an interesting thing to test out. And the other thing is, you're not really... Are you using separate instances of these on different threads, and you're never combining threads?
Yeah. So that's really important. If we're going to use single-threaded allocators, we have to make sure that they're only used on individual threads. If you start using these allocators on different threads, your app's going to crash and burn hard.
Okay. So you don't have a multi-threaded processing graph?
We do not. No, single-threaded. We're making plugins, so we're hoping that the host is going to figure that out for us. Yeah.
It's probably quicker to do it on a single thread.
Yeah. Thanks.
Just a quick comment. So I was actually talking about this to Anthony Williams, who wrote the book C++ Concurrency in Action. Don't know if you've heard that name. And so he's done that kind of stuff. And he told me that, the thing that you mentioned at the end with the multi-threaded thing, that what exactly his approach is. So he does have a lock-free allocator that has this approach where you have some kind of watermark. You kind of say, and it could even be parameterizable, are you get close to X% of what you have currently allocated? If yes, the background thread kicks in, allocates more memory, and then you slide it into some kind of lock-free thing. And so he apparently used that in production. So that's definitely a thing, not just an idea. Cool. I've never implemented that myself, but maybe
it's always
cool.
good to hear that someone's done it, because that means it's possible. It's not going to be foolproof, right? There's a possibility that by the time that memory comes back, you've already run out of space. But
but
that's
I'd imagine that there would be a way to configure that. So unless you just allocate lots of memory really quickly on the real-time thread, you might be able to just kind of parameterize what the threshold is for this watermark. Right?
Yeah, we're not doing that. Obviously, don't go crazy. Don't just start allocating everywhere for the fun of it, because this is still taking time, and we still want to be fast on the audio thread. So, we actually don't do a lot of allocations, but when we need to, it's really convenient to just be able to do it.
Oh, hi there. So kind of 2 questions in one. I mean, firstly, from the point of view of plugins, which I imagine a lot of people here are doing. I don't know, some of you will have seen the talk the Soundwide guy gave yesterday about the contract between the plugin and host, and audio threads. Once you've got multiple instances of a plugin, the host can be pretty hostile in terms of what it can do to you threading wise. And then also I just wondered about sort of lifetime and scope, that these allocators will very often have a sort of lifetime and a scope of their own, and I wondered how you managed the sort of setup and tear down of those, so you don't get an allocator vanishing from existence and potentially leaving some objects hanging that you think are still alive. Those sort of knots you can tie yourself in with C++.
So I'll address the second point first because it's easier. So like I said, there's this way of setting a global default, but we're obviously not using that. It would be very easy then to sort of instantiate one of these on a different thread and accidentally use a single-threaded allocator. So we just simply, at the top level of our audio object, the first thing is a memory allocator. And everything else, we just pass it down as a reference to everything, which is a bit annoying, but it just feels safer to us. Good for testing as well, because you can then plug in different allocators in your tests, and you can track things.
So then the lifetime of the allocator is the lifetime of that audio object, and it's safe from that point of view.
Exactly. The first point, what do you mean? Like, so you're talking about the host maybe using our running our plugin on different threads at different times.
Yeah, and different instances as well. So for instance, some hosts will have a thread pool and then load balance across that, and then one instance might pop up on one thread in one process callback, and then a different thread in a different process callback.
Yeah,
and
another really good reason not to use a static, memory allocator, but to have one. That's the nice thing about these; they are as local as you want them to be. You can actually have different allocators for different uses within the same area of code, and yeah, keep them local, keep them on the stack.
Okay, thank you.
Dave's got another one.
What are your use cases for allocating in audio threads? Why don't you just know beforehand?
Well, yeah, we've got this configurable graph that you can mess about with while the plugin is running. We have another couple of use cases that I'm probably not supposed to talk about in detail. But there are loads of use cases. Like I said at the beginning, if we have MIDI buffers, if we have something inside the graph that's generating MIDI, we used to just allocate a huge one and pray. This is equivalent to that, but we can use the same allocator in different places. And we're not, if we do that in 5 places where we allocate large buffers in praying, and we only use one of those, then we've wasted a lot of memory. Here we can compress everything down into a single block of memory. But yeah, it is actually surprisingly useful sometimes to, have a map, to store a little bit of metadata about something that's happened in your graph as it goes through. Adding vectors of particles for a granular synthesizer. Be creative.
Have you considered running some sort of benchmark that pushes your application's use cases to the edges of the parameters to sort of inform how big those chunks of memory should be, and then maybe put your finger in the air and add a bit to that?
Yeah. We haven't got those. Most of the time what we do is we have a nice configurable graph and we set it up somehow, and it might change a little bit over the lifetime. In an individual product, it might change a little bit in its lifetime, but generally not radically. In the products that we release, we're not tearing everything down and rebuilding things. And, one day we might start doing that, and I think it would be a really good idea for us to really push. Just say how much space do we generally need to use if we're being really aggressive. I think our pool of memory is 2 megabytes. It's pretty tiny. As I said, we're not being profligate and just going ahead and going crazy with this. We still care, and we still try not to create things that don't need to be created. But yeah, I think that'd be a good idea to really push it in some tests and see how far we can go. It's a good incentive as well to slim your objects down. I found as we started using this thing that certain objects were just way too bloated. They didn't need to be that large, and there were ways to slim them down. And you can instrument your allocations to find out, where is most of this space being used. So that's another useful thing. You can just create your own little tracking resource and insert it somewhere in the chain. So. Oh, Fabian's at the back there. Just going.
So I use the monotonic allocator a lot. I've kind of not used the slab allocator back with a free list because although it's lock-free and weight-free, it's still unpredictable, right? And so am I just being paranoid? Like, what is the worst case?
Probably not.
I don't know.
So yeah, I mean, we're lock-free, we're wait-free, but as you say, like as the program progresses and things happen that may be unpredictable as a user changes things, yeah, you're starting to get into an area where you might be taking longer than you should, and it's hard to test that ahead of time. The reason for the pool and then the free list is that we tend to, large allocations are very, very rare for us. So the free list is there as a backup. The pool is generally kind of 0-1, as long as it's not needing to get more memory for itself quite frequently. And as I say, we tend to kind of allocate some stuff, and that's mostly it. It's basically 0-1. You jump to the slab, and then you jump to the slot, and that's pretty much consistent. So, yeah.
Any other questions? I think that might be it. Oh.
Yeah, we had an online question, a very detailed question. Someone said it'd be nice to use monotonic buffer resource to insert into containers like stud map in real time, but there's no way of knowing how much memory to allocate to support n elements, as we don't know how large internal map nodes are. Do you know of a workaround? And they are also asking if you know, do you use node-based containers in real time?
Yeah, that's a good question. We don't actually know how the standard containers are implemented, so we don't know how much extra stuff is in there when we put something into a container. It kind of comes back to that final problem I mentioned. Like, ultimately, there is no true way to know ahead of time that you're not going to exceed the area of memory you've designated. So I think this just reaches a point where you have to test your product, test it under all the conditions that seem like they could potentially happen, and go for it that way. But I think that's roughly where we are. If you're doing dynamic things on the audio thread, that's roughly where we are now anyway. This is more ergonomic, potentially more performant, but that final problem still remains, that if you run out, you run out.
I think last question.
It's not really a question, it's just a comment about the last question, if that's okay. I found that if you need to have an associative container like map and set in real time, you often don't need actual node-based containers, but what instead you can do is you can use something like boost flat set or boost flat map, which provide you exactly the same interface, not necessarily the same complexity guarantees, but internally it's just the vector basically, and everything's contiguous. And we actually added those to the standard now as well in C++ 23. So that's what I would suggest if somebody needs map and set on a real-time thread. Don't use the node-based versions, use the flat versions.
Yeah, I think Boost just came out with a new flat map as well, which is supposed to be good. Thanks.
It's a lot better for cache coherency as well.
Yeah, okay. Yeah, I forgot to answer that second part of the question, so thanks for picking up on that, Timur.
Well, thank you, everybody. Thank you, Tom.
Thank you.